All right, so we were in the process of testing the endpoints to determine the interval of convergence once we knew the radius of convergence was 2. So we had to test 3 and 7. Okay, so we plugged in the 3 into the original power series for x, and 3 minus 5 gave us -2. All right, so here what we have to do is a pretty typical thing. We have a negative number inside the parentheses to the nth power. You want to separate the alternating piece of that from the magnitude generating piece. So with the correct notation, bringing it all the way down each line, it's a little bit of writing, a little bit of work. -2 to the n is -1 to the n times 2 to the n. Okay, all over n times 2 to the n. And now, what can we do with the 2 to the n's? Yeah, sayonara. And then we got to be careful, because I have -1 to the n plus 1 times -1 to the n. Is that still an alternator when we combine them? Well, let's see. When we have the bases the same, we add exponents, don't we? So it'd be n plus 1, so 2n plus 1 all over n. Is 2n plus 1 an alternator? No, we saw that last week. 2n plus 1 is always an odd number. So -1 to an odd number power is always negative. So the fact that that's always negative means you could really pull it out front as a -1 or leave it in the top. It doesn't matter. But you're really essentially now simplifying it down to negative times that. And what do we know about that guy? That's your hallmark divergent. Yeah, that's the divergent harmonic series, the P series. Okay, so what that means is we cannot include 3. We cannot include 3. Sorry, as part of the interval. It's going to be a parenthesis there, and then we do the same thing for x equals 5. Oh, I'm sorry, 7. 5 is the center. We get 7, and for that we get the sum from 1 to infinity. -1 to the n plus 1. But now when we plug in a 7 for x, 7 minus 5 is just 2 to the n. Just 2 to the n. All over n times 2 to the n. And now your 2 to the n's divide out totally on their own without any manipulation. So we are still left with the alternator, -1 to the n plus 1 over n, which then means now it is in fact an alternating series, right? And so remember, for the alternating series, all we have to do is look at 1 over n. What's left? 1 over n decreases and goes to 0. And goes to 0. That's all you need to show, those two things, or say those two things. So this one converges. It's your conditionally convergent alternating series. And then so finally, the interval of convergence. The interval of convergence slash, if you want to call it, convergence, let me spell that right, slash domain is 3 gets a parenthesis, 7 gets a bracket. So for all of those x values, that power series up there represents perfectly, not approximately, with infinitely many terms, some particular function. Okay? We don't know what that function is. But you could certainly graph it for multiple terms in that window from 3 to 7. And the more terms you graph, of course, the closer it's going to start looking, bless you, like what the graph of the function it represents is. Okay? So that one will require a little bit of work. And this would be like a free response question where they kind of walk you through, like one part would be to find the radius of convergence. Part 2 would be like to find the interval of convergence. So you'd have to know to test your endpoints on your own. All right, any comments or questions on that? All right, let's go ahead and do the rest of them. This one here, x over 3 to the nth power. You might recognize these right away as something else, and you wouldn't have to use the ratio test. What do y'all notice about having a fraction to the nth power? It looks like it could be what? Geometric, right? Geometric. And what do we know about geometric series? We know that if the ratio is less than 1, it's going to converge. So will this thing converge at x equals 3? 3 over 3 is 1. 1 to the n doesn't work. What about at 2.9, though? If x is 2.9, will it work? Yeah, 2.9 thirds is less than 1. What about 1? Yeah. What about 0? Yeah, 0 converges to 0. What about negative 2.9? That would also work. What about negative 3? No, that makes it negative 1. So right away, you know that the interval of convergence is negative 3 to 3 because it's a geometric sequence, okay? And you know that the absolute value of x thirds, which is the ratio, has to be less than 1. So you immediately get to x is less than 3, then you get your radius is 3, and you wouldn't even have to test the endpoints if you make a geometric series argument. But let's take the longer route and say, okay, what if I didn't recognize it as a geometric series? You can still do the ratio test. So let's go through that one more time and see what it looks like. We'll get the same result, but just a little bit more work. So we take the limit as n goes to infinity. Now we get x thirds to the n plus first. I'm just going to go ahead and divide it by now, truth quotient, x thirds to the nth. And if you do that, you get the limit as n goes to infinity of the absolute value of x thirds. Well, x is a constant, right? We're treating x as a constant because n is the variable, and 3 is a constant. So what is the limit of a constant? A constant, right? So that limit equals the absolute value of x thirds, which now by the ratio test, you force it to be less than 1. So notice that's the same thing you would get if you recognized it as a geometric series right away. Just a little bit more fun to be had. All right, now remember, here's our goal. What's the center of this one? Can you tell? 0. Yeah, because if it were something other than 0, it would be x plus or minus a number. So the center here is 0. So our goal is to get x minus 0 less than some number r. Well, that's the same as just absolute value of x is less than r. X minus 0, same thing. Well, all we have to do then is multiply by 3, and you get that, which is the same as this. So if you didn't realize it before, now you could say, so the radius of convergence is 3, and then you'd have to test your endpoints. So let's come up here now and test the endpoints. Or actually, if the radius is 3, here's what you might want to do. I always, again, like to draw the little number line. So I can go 3 units to the right of the center and 3 units to the left of the center. And this one's symmetrical around 0, so it's pretty easy to come with negative 3 and positive 3. So now I'm going to come up here and test the endpoints. Testing the endpoints. We get, I like to do the negatives one first, so I just go from left to right. So if I plug it in, I get the sum from n equals 0 to infinity of negative 3 over 3 to the nth power, which is from 0 to infinity of negative 1 to the n. So we do have to write all this out. Now, negative 1 to the n diverges by the nth term test. It actually starts as a positive 1, and then it goes positive 1, plus 1, minus 1, plus 1, minus 1. So the nth term test. And then we do the other endpoint, x equals 3. Plugging it in, we get the sum from 0 to infinity of 3 over 3 to the nth power, which is the same as 1 to the n, which is the same thing as 1. So that one totally diverges, right? Also by the nth term test. Diverges by the nth term test. And then, so if you hadn't figured it out yet, we can't include either one of the endpoints. The interval of convergence slash domain, same thing, is just negative 3 to 3 non-inclusive. So when you do the ratio test and you test the endpoints, a little more work to be had. You could have not included the endpoints by doing a strict geometric series argument and saved a little bit of work. But that doesn't happen that often. You're not always given something that looks like a geometric series. So the ratio test, when in doubt, just use the ratio test, and it should work. All right. We got 2 more here. Let's take a look at this fella. Is it a power series, first of all? If so, why? There's an x, right? There's an x in it. So it's a power series that's got an x. What's the center? 0. Yeah, center is 0. Because if it weren't, it would be something like x minus 3 to the 2n plus 1, and then the center would be 3. Or if it were plus 3, the center would be negative 3. Okay, so it's just x, so the center is 0. So it's an alternating series as well. You might spot the alternator there. So when we do the ratio test, Here's what it's going to look like. The limit as n goes to infinity. We don't need the alternator in the ratio test. So when we replace n with n plus 1, just a little note right here, 2 times n plus 1 is 2n plus 2 plus 1, which is 2n plus 3. So that's what you get when you replace n with n plus 1. So this becomes x to the 2n plus third power all over 2n plus 3 factorial. You're physically replacing n with the quantity n plus 1, and then you would have to distribute the two and combine like terms. So that's actually the n plus first term. It looks like n plus third term, but it's really the next term. Okay? Times the reciprocal of the given one, which is 2n plus 1, all over x to the 2n plus 1. Factorial. Thank you. Yeah, that's pretty significant. Factorial. Factorial. Okay. So now we'll do our little fun algebraic, kind of like speed stack cups, condenses down to something. Let's look at the powers of x first. You have how many more in the numerator now than the denominator? 2 more, right? So it's x squared. And then the 2n plus 3, when you write it down recursively, it's 2n plus 3 times 2n plus 2 times 2n plus 1 factorial. So you actually have two factors here that you have to write out. Okay, so now we're at the point where we have x squared, which remember we're treating as a what? A constant. So n is our variable. So I have a constant. If you want to think about what we have here, we have essentially a constant over a 4n squared as n goes to infinity. What happens to that? It goes to 0, right? A constant as n goes to infinity over 4n squared goes to 0. Is 0 less than 1 always? Yeah, it's always less than 1. And so what that means then is it doesn't matter what x is. X can be any number, and it's always going to converge to 0, which is less than 1. So it'll always converge. So the radius is what? If it converges for all real numbers, the radius is infinity, yeah? And the interval of convergence / domain is negative infinity to infinity. So that one is very similar to e to the x, very similar to sine of x, cosine of x. It converges for all real numbers. Okay, so for infinitely many terms, it perfectly represents some function. We don't know what that function is, but we could graph terms and see its graph if we wanted to, maybe on some other day. All right, do we need to test endpoints on that? No, because infinity and negative infinity are not really endpoints. And if they were, it would converge there anyway, because it converges for all of them. All right, last one of this little section here. N times x minus 3 to the nth power. It's a power series. What's the center? 3. So yeah, I always want to identify the center first. I kind of didn't do that on part B, but the center is at 3. So does this one converge at 3? Yeah, we know before we even start, it converges at 3. That's always a given. It's going to converge and be the same value at the center. Are there other values? Well, we shall see. Let's do the ratio test. Go ahead and write it out. Say what you're doing. The ratio test. The limit as n goes to infinity, n plus 1 factorial times x minus 3 to the n plus first. This one doesn't have a ratio itself, so there's your numerator, and I'll just divide by the nth term in the denominator. And absolute values. Don't forget those. Even if there's no alternate, you want to put them on there. Okay, now we do the fun part. We simplify. N plus 1 factorial is n plus 1 times n factorial. So it just is left with an n plus 1. And there's one more factor of x minus 3 in the top and the bottom. So that's all we're left with, all that over 1. So again, that simplifying part, if you're not sure what I'm doing there, I would recommend coming into tutorials and I'll talk you through it, because that's kind of the fun part and the critical part, really. So again, because we have a limit as n goes to infinity, and we're treating n as the variable, and therefore x plus 3 is just treating as a constant. So you could really bring it in front, and it becomes the coefficient of n. But as n plus 1 goes to infinity, that goes to infinity, and what's infinity times a constant? Infinity. So this equals infinity. Is infinity less than 1? No, so you can write it like that. Infinity is not less than 1. It's a less than sign with a line through it. It means not less than 1. So, do we say this series diverges for all x? Except for 3. Yeah, so you could say it that way. So the series diverges for all x not equal to 3. That's one way to answer the question. Okay, and you have to remember that on your own, that it converges at the center. Or you could say the radius of convergence is what? Is 0. Yep. And there is no interval. Okay? No interval. You could then say the series converges only at x equals 3. So all those kind of say the same thing. So that's where you really got to be careful. When the ratio test fails and you get that it diverges, you have to remember that it does diverge for all x except the center, because that's always true. That's where we're anchoring it, and so they share the point there. All right. Questions on that? I want to retreat back up here and do something with e to the x, okay? Because we said e to the x converges for all x. So we'll come back up to example 1. If it truly is an identity, let me go ahead and bring this guy over here where there's room. If it truly is an identity, then we can actually use it as a replacement for e to the x. Okay? They're one and the same. So let's go ahead and do this. Let's go ahead and take the derivative of both sides with respect to x. What is the derivative of e to the x? E to the x. Let's see if we get that. So the derivative of 1 is 0. The derivative of x is 1. Then we get 2x over 2 factorial plus 3x squared over 3 factorial plus 4x cubed over 4 factorial plus. Now here's the really nice thing about having the nth term. We can take the derivative of it as well. That's going to be n times x to the n minus 1 all over n minus 1 factorial plus dot, dot, dot. Okay? And we'll be doing that in the next section or later on in this one. Now let's simplify. 0 plus 1 is 1. 2x over 2 factorial, that's just x. 3 over 3 factorial is just 2, or 2 factorial. 4 over 4 factorial is just 3 factorial. Do you notice the same pattern? It is. It's exactly the same. But here's what's different. The nth term now is slightly different than the nth term above. But what's important to note is they capture the exact same pattern. X to the n over n factorial, and, oops, I didn't simplify this one. This one would be x to the n minus 1 over n. What did I do? Oh, yeah. I made the mistake up here. This is n times x to the n minus 1 over n factorial. My bad. This is supposed to carry through. And then n over n factorial is n minus 1 factorial. Sorry about that. Okay, so now if we wanted to write this in condensed form, you would have to be very, very careful because your nth term, your rule of sequence is a little bit different. So it would be x to the n minus 1 over n minus 1 factorial. And now to start off with the value of n that gives you a 1, would we have to start at 0, 1, or 2, or what? What starting value of n when I plug it in gives me a 1? It would have to be a 1, right? When you plug in a 1, 1 minus 1 is 0. You get x to the 0, which is 1, over 0 factorial, which is 1. So notice these two series are exactly the same. They are equivalent to each other, this one and this one, even though they have a slightly different look because the offset is accounted for in the bottom, the starting value of 1, which makes sense. We lost the first term when we took its derivative, so we have to start at 1 instead of 0. Okay, so you got to be careful. When you have the nth term listed like this, you do not need to specify the starting value of n. You just capture the pattern somehow. So you can really have x to the n minus 2 over n minus 2. As long as those two are the same, you've captured the pattern. But when you write it in condensed form with the sigma, now all of a sudden it's super important to have that starting value of n, okay? So as we move forward, that's what we're going to be doing. We're going to be taking derivatives and integrals of these polynomials that represent these functions, and they're going to behave the exact same way, okay? But for now, we're still in the process of trying to determine the domain of these power series. For what values of x they perfectly imitate the functions that they're representing. All right, so here's the summary. The Taylor series centered at x equals c. F of x, the function f of x, is equal to, not squiggled, and notice we are generating the terms the exact same way. The y value plus the derivative times x minus the x value, and then the pattern kicks up, just like it did for the polynomial. So the nth term is the nth derivative over n factorial times x minus c to the n. Okay, that's going to be called a Taylor series, and if the center happens to be 0, then they'll call it an approximate Maclaurin series. Okay. So let's answer one more question, and then we'll call it a day. We now use an equal sign instead of an approximation sign. Do you know why? Of course you do. Why? It's equal for all, but why does it equal for all? It's not a finite number of terms. It's because of this thing right here. Because it goes out to infinity. That's why. Okay? Because we use infinitely many terms, we can use equal signs. All right. That's it. I would participate in Spring Fling the rest of the week. It's going to be fun. And, yeah, if you didn't turn in 9.2 today, turn in tomorrow. And remember, 9.3 worksheet is waiting for you on the Worldwide.